you very much. Recording in progress. Got it. Great. Yeah, welcome everyone also from my side. I'm really happy to be here today and talk about the graphical language server protocol and also a little bit about related technologies such as the model server. But we really wanted to divide the two aspects, as Dominic said, between the theoretical or architectural part from the actual practical part that Nina will cover. So to give you sort of the room to understand the main goals and the main architectures about the different technologies that are involved. And then in the second part, you really can focus on how this looks like in daily work in code and how you can incrementally develop your editor, diagram editor. Right. So before I start, just what I just mentioned, the two main parts, I think basically I already covered all of that. So I will just skip that directly to the motivation. So as Dominic said, there is quite a lot of modeling technologies out there. And I think at least a few of you already heard a few of them when you visited attended the model engineering course, like the Eclipse modeling framework and many other XTechs and many other technologies of this ecosystem. And they are all are pretty much tied to the traditional Eclipse rich desktop experience, right? But this is a little bit dated and dusty, and more companies, tool providers, and especially adopters are pushing towards going into more modern look and feel to get a better user experience. And this obviously nowadays means that we want to go towards web-based user interfaces where we can leverage the UI technologies, HTML5, CSS, SVG, to really provide a modern look and feel and to get a better user experience and to benefit from the powerful capabilities that they offer. At the same time, of course, however, we want to keep the capabilities that modeling tools nowadays, or in the last 20 years actually, provided in terms of you all often know them if you know Eclipse or IntelliJ or many other IDEs. They are pretty powerful tools, right? So they have support for programming languages. They might have support for model-based configurations where you have complex forms. You can validate the data model that you're editing using those forms. And you might use graphical editing, diagram editors, and so on, such as all shown here on the left-hand side. So basically, these are two little bit competing things. So on the one hand, we want to do the user interface all over again to provide a more modern look and feel, but at the same time, we want to keep the powerful capabilities that these tools often allow. And of course, it's clear that you can't bring all these functionalities into the browser, but that you have to separate the user interface running in a browser with backend services that really then encode and do the heavy lifting of all those very powerful technologies or capabilities that IDEs and modeling tools are offering. So the architecture that really evolved from that demand to have, on the one hand side, modern look and feel in running in a browser, but keep those technologies and keep those powerful capabilities, is to separate the user interface from these backend services, so that basically you take a lot of the heavy lifting and capabilities into separate backend services and let those services only communicate with the front end. That, of course, immediately requires some sort of communication between the front end and the back end in terms of some sort of protocol. And at the same time, this protocol needs then to be interpreted not only on the front end, but also on the back end, where there are these services that then translate that into some sort of underlying data model, whether it's a program that you're programming or whether it's a model that you're editing. And that also means that they need to communicate and work together on this data model. And therefore, very often there is some sort of, we call it model server, which is sort of like a component that manages the runtime state of some sort of data model in the backend. But we will come to all of these things that you see here on the left a little bit more in detail later. But that's essentially the overall architecture, basically summarizing, putting a front end up that has as least as possible know-how about the complexity of programming, language editing, of graphical editing, and so on, and having a component that is capable of coordinating the runtime state across multiple services that may operate on them. Before we go into the details about the graphical language server protocol, which is a framework for editing or for creating diagram editors, we talk a little bit about the language server protocol, because this was really the first use case where this architecture has evolved from, and it's also hugely popular. So basically, more or less whatever IDE you're using today, it most likely will support the language server protocol, or even will completely be built on the language server protocol. So 1 second, I will just reposition my mobile because I get a little sound in my headphones. So one hugely popular code editor that you're, I guess, all familiar with is VSCode, as already Dominic mentioned. And VSCode is entirely built on top of the language server protocol. It was even one of the main drivers to invent it in the first place. So we'll talk a little bit about that to grasp the ideas behind it, the rationale, why it's built this way as it is, and then adopt this towards the diagram editors, which have, of course, a little bit different settings, characteristics, and requirements. So language server protocol. Essentially, the language server protocol, it has exactly the same goal that I just summarized. It was mainly motivated by the development of VSCode. And this motivation is sort of bringing the feature-rich text editing capabilities with sophisticated language support into a browser, sort of enabling web-based UI technologies being used, but still offering this very sophisticated language editing features. Of course, when you think about language editing features, and with that I mean, for instance, that you get autocomplete when you start typing, that you get immediate feedback whether something you type corresponds to the grammar or not, that you get detailed error messages if something is not valid or so. So all of these features really require a very deep understanding of the actual language that you're editing, right? So when you work in a Java program, obviously you will have to have different language support than when you're editing, I don't know, Ruby or Perl or Go or whatever. So that means basically they have to be language specific on the one side and really do a lot of heavy lifting, like parsing your text, building an abstract syntax tree, indexing your program, and so on and so forth. And what's really important to understand, actually, I'm not sure if you have thought about it ever, but if you're, for instance, writing in Java or in TypeScript, it's not actually just sufficient to look at the file that you're currently editing, but you need to look at an entire workspace or project or module, its dependencies and so on, because this determines whether you can, for instance, import another class and then interact with this other class and so on. So it's really something going way beyond just analyzing the text file that you're currently viewing. And sort of this is of course the requirement that we want to maintain, but we want to now support the web-based technology stack. And that means we have to pull out these heavy and sophisticated capabilities from the front end, because it's clear that the browser can't easily do that on its own. So the basic idea behind the language servers is to really pull out these capabilities and encapsulate it in a so-called language server, which basically then does all this heavy lifting, like parsing, abstract syntax tree, and so on and so forth, and have then a protocol that talks to a language client. You can think of it as the editor UI. That should be as generic as possible. So for the language client, for the editor, it shouldn't be anything different whether you're editing Java files or I don't know, Rust files. But the only thing that should be different is actually the language server. And that's really the main idea. Between them, there is a protocol that transfers the language specific know-how in a very UI-oriented way on a need-to-know basis from the server to the client. One aspect that is also a main motivation behind the language server architecture is also and we will see that also for the UML editor project that we will all be working on, is that we not only want to basically separate those two just to allow running in the browser, but also to allow reusing existing implementations of language support. So for instance, when VSCode came to the market, it was obviously very late to the IDE market, because the IDE market exists already since, I don't know, 20 years or so. it wasn't possible for them to catch up with all the language support that you would expect from a code editor. So they had to find a way to allow other existing language implementations for Rust, for Java, for I don't know, HTML and so on, to integrate with VS Code with the least possible amount of effort and without having to rewrite everything from scratch again in the respective language that VS Code is built with. And that's a completely different approach than any other IDE that has been on the market until then. Because if you write language support for Eclipse, you had to do it in Java. If you write it for IntelliJ, you had to do it in Java. If you write it for Visual Studio, not Visual Studio Code, but Visual Studio, you had to do it in, I don't know, C#, I think, or any of the .NET languages, I guess. So that's a really completely different way of looking at things. One thing that is very important about the protocol is that it's very, very UI oriented. So it does not reveal anything about the actual programming language internals, but really focuses on what is needed in order to provide the language editing support. So that means, for instance, the editor and the language server, they don't talk about classes, functions, methods, variables, and so on. All they talk about is files and locations in those files. And that there might be some, I don't know, some completion proposals for an autocomplete that someone invoked on this character position. And the reason for that is because this makes it extremely versatile and not depending on any structure that one language might have and another language does not have, which in turn allows the client to be extremely generic and really focus on the UI only. So let's look at an example conversation between the client and the server. So first of all, the development tool, so the editor, notifies the server that a document has been opened by the user. So this allows the language server to start creating an in-memory state of this document. And from this time on, whenever the user changes something, the client will notify the server that some changes happen. Why is this necessary? Because of course, when you start editing somewhere, you might not have saved the file, but it's just an in-memory state of the document. And you would expect that also for in-memory states of the document, you receive corresponding, I don't know, validation errors and corresponding auto-completion suggestions and stuff like that. So the client and the server have to synchronize on the runtime state of a document. And at any point in time, the language server can then notify the client that there are new diagnostics. Diagnostics are messages that are sent. So for instance, these red squirrely lines are sent in terms of diagnostics to the client. There is now an error from character, I don't know, let's say 20 in line 14 with this text. And it's basically a severity error. And with that information, without having to understand anything about the language, the client and the editor can actually already show this information as you would expect from an IDE. And that's what I really meant with UI oriented. It does not tell the editor, the server does not tell the editor that there is a variable missing or something like that. It's not necessary, right? The only thing that is really required is that there is some error message from this area to that area, and that's basically it. Still, you have a lot of more functionalities, like here, this peak problem and so on, but those are all the time just a server telling the client, you can here peek at the problem, and then you might, I don't know, jump to a different area of the text file, but that's not really something language specific at all. And the same is also true for these completion items. To the client, it's basically just a label that you can add a string here, and that's the level where the client and the editor and the server communicate on, and not like that's the some sort of variable that you access with this or that scope. Right, and with that, basically with that mechanism, many features of an IDE or of a good code editor are covered. Of course, for each of those different features, there is dedicated messages that the client and the server can exchange, like going to definition, even doing refactorings and stuff like that. Language server protocol is really popular. So it's either way, whether you are dealing with GLSP in the future or not, you will, if you are somehow related to programming in the future, always will come across the language server protocol. So it's super popular these days, mainly because of the advantages that we just highlighted. Originally, it had been introduced for the development of Visual Studio Code, which is an HTML-based code editor, but it's open source. So the language server protocol is actually open source and currently considered to be the de facto standard to develop or to at least integrate language editing capabilities in editors. There are many hundreds of different language servers available, most of them open source, some of them proprietary for all possible languages that you might want to use. And there is quite a number of different clients available that you can use. So it's Visual Studio, VS Code, obviously, but even the traditional IDEs like Eclipse, IntelliJ, and also Sublime, even VI has support for language servers nowadays. So you can use actually the VI editor and benefit from the same language features that you can benefit from in Eclipse or in VS Code. For building language servers, there is also, of course, frameworks available. I don't want to go too much into detail. I just mentioned here Xtext, because if you attended the model engineering course last term or any time before, you might have gotten in touch with Xtext, which is a framework for building domain-specific languages, and they also have support for language server protocol. So you can build quite easily a language server based on an Xtext grammar nowadays. Right, that is basically the very brief introduction of the language server protocol. So I didn't go into any of the details of how it really looks like, but I really wanted to focus on the basic idea and the architecture behind it. Now coming and adopting that, coming to diagram editors and adopting that for diagram editors. Essentially, when you think about it, you want to bring diagram editors from, I don't know, Eclipse, SWT and GMF technologies, so these old, super old technologies. You want to bring those diagram editors onto a web stack as well. You actually run into very similar issues as if you want to do it for programming languages. So one of the similarities is, for instance, that it's not sufficient to look at one diagram because typically you have a diagram that edits a sub part of an underlying model, and then you can open a second diagram and this edits an potentially overlapping part of the same underlying model. So it's not sufficient to just look at one diagram in order to provide good editing feedback, like, okay, you shouldn't add a connection here because there is already one. Maybe you can't see it in this diagram, but it's there. So therefore, you need to have a full model understanding in your editor. Obviously, that's something already very hard to do if you only do it in a browser. Also, of course, diagram editing is much more than just rendering and having a UI for it. There is very often very complex model logic in the back end with validation rules, with specifications of which actions are allowed, which types of model elements exist, how can you connect them, and so on. And this is also something that you don't really want to implement everything in a browser, especially not re-implementing that again in the browser, but rather you want to reuse existing model and diagram implementations of the editing logic. So the backend should be really independent of the front end. So essentially the same as we just talked before in LSP. However, there is also quite a lot of different things or things that are different between diagram editors and textual or programming languages. So first of all, when you think about a text editor used for Java editing and then for Rust or TypeScript editing, pick your favorite programming language, then and you think about what can you actually change. Of course, you could think about, okay, I can add a class in Java. I can add, I don't know, not a class in a language that is only functional, for instance. But that's actually not when you think about how you really edit the artifacts, it's not the way how you edit them, right? So in text editors, you basically insert and remove characters at line positions in text files. That's basically it. But it doesn't matter whether it's Java or whether it's I don't know, Rust. So essentially, this part is always the same for all programming languages. And this is, for instance, not the same case for diagram languages. Also, rendering flexibility is really something that is completely different. Text editing will always look the same. So you always will just deal with characters. So you will have to show characters, a cursor, and then you remove or add characters. It's always the same. But for diagrams, they, depending on the diagram language, they look completely different. So you need some sort of different ways of showing things. And that brings you to a so-called impedance mismatch, which means in order to show a diagram like that, you typically need to read artifacts, interpret them, and then render them. So there is a step, this interpretation step in between from a serialization format to a diagram, which is obviously also not given for text file, because if you read a text file, you can directly show it, done. But for diagrams, there is this interpretation step in between. Right, and last but not least, I already mentioned this generic editing difference. So text is always generically edited in the same way, but diagrams not, because some languages allow you to add a, I don't know, a connection between these two elements. Others don't even have a connection that you can add between elements. So it's really depending a lot on the diagram language. And these three differences have, of course, quite a heavy impact on the architecture of how you can adopt the language server protocol. So first of all, you can't just use the language server protocol for diagrams. That's just not possible because it's this text-oriented thing, the language server protocol. And second of all, you can't have the same separation of concerns between client and server because of these differences. But let's look at the differences in general. But before, let's introduce the project that we are dealing with. So basically, now we've realized we want to have something like the language server protocol for diagrams, and we can't use it as is. So that means we need something new, and this new is called Eclipse Graphical Language Server Platform, GLSP for short, with the goal of applying the architectural patterns of the language server protocol, but applied to graphical modeling in order to unlock the same benefits that we had with the language server protocol for programming languages, but of course for diagrams. GLSP is an open source project managed by the Eclipse Foundation, or not managed, I think the correct term is governed by the Eclipse Foundation, managed by its open source committers, like for instance, Nina and myself. And it's available on GitHub, obviously, so you can check it out. You can, we are really also, as Dominic said before, really inviting everyone to look into the source code when you use it, even contribute to it, provide fixes if you want to, and really benefit from the fact that it's open source. Basically, what it offers you is a framework in order to develop browser-based diagram clients, whereas the front end is really focused on the UI and rendering part, and the back end is really focused on the modeling aspects like modeling rules, editing rules, validation, and stuff like that. In addition, of course, it defines a base protocol that they exchange. So that's very similar to the language server protocol from the idea. And what it also adds is so-called platform integrations that allow you to seamlessly integrate a diagram editor that you've built with GLSP into different platforms like VSCode, Eclipse Thea, any Electron app, or even a plain browser app. You can even integrate GLSP editors into Eclipse rich client applications if you like it. If you are a little bit retro, or you don't have it, or you have a reason really for doing that. So talking about the separations of concerns that the GLSP applies, essentially, when you think about a diagram editor, there is actually quite a number of different capabilities that, or group of capabilities that such a diagram editor provide. First of all, obviously, you need some sort of diagram rendering, so to know that how to actually how to represent a certain type of node in a diagram, like here a rounded corner rectangle with a label inside and stuff like that. So that's rendering. Then you have typically some sort of editing tools that allow you to change the diagram, like you can here click and then add an input pin to some element and stuff like that. While you are changing the diagram, you typically want to have some sort of visual feedback that guides you whether you can actually apply the change or not in a certain scenario. Of course, this visual feedback then encodes in some way already the editing rules, the underlying editing rules that need to be implemented in such a diagram editor. And once you really then apply a change, you have to run the command that modifies the model in the memory. Usually you do that in transactions, and then you expect to have live validation so that you immediately see all errors that might occur during the changes. And in the end, you need the whole model management stuff as well, of course, like serializing and deserializing models and stuff like that. So all of these capabilities are typically traditionally implemented in one component. Now, since we have a client and a server, we have two components. Where do we draw the line in terms of separation of concerns? In GLSB, we chose to draw the line between visual feedback and editing rules. Obviously, because diagram rendering, editing tools, and visual feedback is something that is very UI oriented, and you want to have immediate feedback on them. So you kind of would want to avoid to have server round trips and so on. However, at the same time, as I mentioned before, visual feedback already requires some knowledge about the editing rules to indicate, for instance, if you are allowed to do a change or not. So you need to transfer some know-how between those two, and therefore there is dedicated messages in the underlying protocol that they use. So let's have a look at the interaction a little bit in more detail. So in the beginning, when the diagram is being opened by a user, the client sends an initialization request to the graphical language server, usually pointing to some sort of, or identifying some sort of model or resource using a URI or so. What the server then needs to do is, based on this information like the URI, it needs to know where to get the model from. And this can really be an arbitrary model, whether it's an EMF model or even a plain JSON file. It doesn't matter, actually, especially not to the client. In some way, you need to load a model. And what then the server needs to do is to translate this original model source into a so-called graph model. And the graph model is sort of an abstract description of the diagram to be rendered in the browser. So it doesn't matter, it doesn't need to be the full model. It can also be only a subset of an underlying model. So that's something the server can decide on its own. In the end, it sends to the client this graph model, which specifies these are 5 nodes with these different types, and they have these children or child nodes, and they have these connections among each other. That's described in this graph model. And based on this graph model, the client can now render this graph model by translating each node type into SVG based on SVG views in order to produce in the browser an SVG that is then being rendered. For this part, by the way, we are using another Eclipse open source project, which is called Eclipse Sprody for the rendering part. So conceptually, if you think about it, if you're going back to the language server protocol and programming languages where you have just text files and so on, basically what is known to the client and the language server in the programming language case is just a text file, right? Characters and lines. So this is what the concepts that they share, among other things, but mainly this is what they share in terms of common artifact that they operate on. For GLSB, it's really this graph model. So this graph model sort of replaces the text file. It really, you can consider it as an abstract description of the diagram that both agree upon and that both understand. So all the communication is based essentially on this graph model. How and how it relates to this original source model is really only a server concern. So the client doesn't really need to care at all whether this is actually loaded from a database JSON file, 5 EMF models, or just one. It's really only the graph model that interests the client. So how about editing then? We have rendered the diagram. What about editing now? Obviously, the client doesn't know anything about the language or shouldn't know too much about it, but you want to provide things like a tool palette where you can select nodes from, stuff like that, and then apply them. So that's exactly what I mentioned before. Therefore, we have these dedicated protocol messages where, for instance, the client can request tool palette actions, and then the server retrieves them from some sort of registered tool palette item provider and sends those back to the client, and the client can then render a tool palette. However, the client doesn't really understand what a decision node or an automated task or a fork node and all this is. Just for the client, it's just sort of a label And it has a sort of an associated type ID that it knows when the user clicks here. I need to create a node with that type ID, but what it actually is or how it will affect the diagram, not a client concern. So what happens if the user then starts to create a node based on that? So first of all, the client will initiate the node creation tool, which is a client-side tool that provides this, for instance, visual feedback that we are about to create a node. And once the user clicks, then the client will send a create node action back to the server. The server will receive that, forward it to the respective registered handler that takes care of applying this change to the model, will then apply it, but really apply it to the original model. So that's the model that we've loaded from, like a JSON file, diagram, EMF model, whatsoever, but not the graph model, but it will apply it directly to this model again and then regenerate the graph model after the change has been done, and will then send the updated model back to the client. And that will then obviously lead to a new node, hopefully. The idea behind that is that you have a unidirectional event flow, and you can reuse the generation of the graph model, because this function here that takes the source, the model source, and generates a graph model is exactly the same that we've used here before in the initialization phase. So it's always the same function being built again, much easier to implement than some sort of bidirectional synchronization. Right, so much about theory. Taken too long anyway before I gave a demo. So let's switch to a demo real quick. So what you see here is essentially a cloud IDE based on a framework that is called Eclipse VIA. So it looks very much like VSCode. That's because it incorporates many of the aspects of VSCode, but the main difference is that it's truly open source and highly customizable, which is not the case for VSCode in some parts, but it doesn't need to concern you too much. So we have a cloud IDE. What we have here in addition is that we have a diagram editor based on GLSP that is integrated with this cloud IDE, and that is registered for WF files. So whenever I click on a WF file, then a diagram opens, and that just happened. Now just all of these messages happened that I discussed about before. So the client sent an initialization request. The server then read this WF file, translated that into a graph model, sent it to the client rendered it, then the client requested the palette items that exist and so on. And basically now we can start doing stuff. Of course, we can do panning, stuff like zooming and so on. And then we can start to add elements, for instance, like here, I don't know, join node, and then we can start drawing edges as well. So that's basically it. And for each, after each change, the client just invoked the change on the server. The server actually applied it to the original source model, then regenerated the graph, and the resulting SVG has been, or from this graph, the client regenerated the SVG in a virtual DOM, and then only the change DOM nodes will be actually re-rendered. Right. The same is, of course, also true for many other editing things. So for instance, if I now undo changes, then the client tells the server to undo the last change, and then the same regeneration of the graph and updating of the client will happen again, and so on. Right. So what about these visual feedback, and where we need some more understanding about the about the diagram language? For that part, there is so-called type hints. So the client can request type hints from the server, and type hints describe which element types actually have which characteristics. This is, of course, just a generic description specifying, for instance, that the element manual task can be repositioned, it can be deleted, it can be resized, it can contain other element types, and so on. And this is all relevant information in order to customize the editing tools that we have here. So just to give you an example, we can create an edge from this element to that element. So that is basically specified in the type hints, or in this case in the edge hints. But we cannot create an element, a weighted edge starting from here. So here I can click whatever I want, nothing happens. But I can create an weighted edge from this node. And this is really something that is just already allowing the client to interpret certain of these editing capabilities and provide visual feedback that is already correct. And here again, the idea with very UI-oriented way that I mentioned for the language server protocol as well, we don't expose anything real semantic here, right? We just specify the client should know where you can start which actions and which type of actions and where you can't, right? Still, you should remember the actual change really always happens then on the server. So even if the server specifies this is not allowed, but the type hints allowed it, then nothing would have happened. And I can now show you that in code a little bit, just to give you a little bit of an interesting demo. So now I'm going into the, Nina will show much more code than I do, so I won't explain too much about it, but really I go into the configuration of this language, of this diagram, workflow diagram language. This is basically the example that we see here. And here you see that there are these type hints specified. For instance, here we specify that there is a manual task, which is this task, for instance, that basically when you look at here, you see it, that is resizable, that is reparentable, that is repositionable and deletable, for instance. So that means I can move that back and forth. I can delete it and do all this stuff. When I now change that and say, okay, this is basically not repositionable, not resizable, and nothing actually, and then I save that. Just need to reload the type hints, so I need to refresh the browser page. And now if I create an element, I can, oh, I changed the manual task, right? I can still change those and even delete them, but for those, I can't move them anymore. So now the entire diagram moves, which is similar to just panning around here. I can't resize them, so I don't get resize handles, even though I get them for the other elements, right? And I should not even be possible to delete them. You don't see that, but I hit very loudly the delete key just to give you an idea about that. Right. What else? So there is this is just to give you a brief feature overview what GLSP provides. I will not be 100% complete here, but just to give you an idea of which capabilities you will be able to use for your diagram implementations. Just putting that side by side so that I can read that at the same time. So basically, we already talked about zooming, creating elements, deleting elements, resizing, and all that stuff. You can also do things like routing. So when the element is reroutable, you can change the routes and so on. You can do label editing. So when you double click on a label, you can do something like that. You can also provide validation messages. So if I create, for instance, a decision node and then hit validation, you see that there is an error now marked at this element. If I hover over it, then it specifies some sort of error message and so on. It also has some sort of autocomplete editing. So for instance, when I switch into this example where I can then start editing and the server provides some auto completion during that editing, and then even have some sort of validation going on there. So this is all logic that happens on the server. Then you have some sort of auto command, how it's called, a command palette where you can fill certain actions when the user hits control space and invoke some actions, for instance. There is navigation support, so you can register custom navigation types like go to next node. Obviously, that's something that is specific to the language. So the language needs to, we need to understand the language in order to say what is actually the next node from this element. So that's nothing generic, right? So therefore, the server actually replies to those navigation requests and just sends to the client what the actual navigation target is. Same is also true if you navigate between different markers. It's also navigation feature. And last but not least, we have things like auto layouting and stuff like that. Yeah, the rest is, I think, pretty obvious. You have things like marquee selection and stuff like that. Right. just a little bit of a primer already for the thing that Nina will talk about much more, just to give you a basic idea of how the protocol is implemented technically. So essentially you have obviously two components, the client and the server. Both have a unidirectional event flow on the client and the server. And basically this event flow always starts with some action that is dispatched to a handler. The handler can then do something with it, either sending other actions or changing the actual diagram or G model state, as we call it here, which may lead to an update of the G model. And then of course also the views update and so on. And then when the views update, you can also register listeners like mouse listeners, keyboard listeners and stuff like that. And they can generate again actions, right? So in this case, basically when you, for instance, pan here, what happens is that a mouse listener triggers and sends an action to move the diagram, for instance. Of course, now how does the communication with the other side work? The two action dispatchers on the client and the server, they are actually connected with each other. So whenever there is a handler registered on the opposite side, then this action is not only handled locally, but also dispatched to the other side using JSON RPC. And then, of course, this way you can also trigger an action handler on the opposite side, like on the server. So when we click here and then click again, the mouse tool will trigger a create node action. Obviously, this happens on the client, but the handler for the create node action is registered on the server. So this action will be sent over the wire, processed by the server. This will lead to a new generation of a G model, which will then trigger the model submission, which sends back an update model request or update model action, which then again is handled on the client, which then updates the model and the views and so on and so forth. So that's basically how this communication roughly works. I've already mentioned the integration then into tool platforms. I think it's not so relevant for now for this course, but just to specify, this editor here can then be reused in multiple platforms, like here in Eclipse Thea, but also in VSCode or even Eclipse. I won't go into a demo here, just to save a little bit of time. Just to give you an idea what this platform integrations usually take care of. Usually they take care of everything that goes beyond the actual diagram boundaries. So things like populating the errors here into a problems view is one example, but also things like integrating with global actions like undo, redo, copy, cut, and paste and stuff like that, or sometimes even the right-click menu, because actually the right-click menu triggers a context menu, or the right click triggers a context menu, and this should be the native global one and not a different one for this diagram editor. So therefore it's integrated with the one here in this example, Thea and so on. Right, so just to recap, before we go really quick, just over one more thing and then hand over to Nina. The main idea essentially is to have this unidirectional event propagation. So essentially not have any synchronization going on, but really a client sends a change request to the server modifies the original source and then regenerates the model or the graph after each change. What's really now interesting, and that's the one more thing that I wanted to mention, in many cases, this model source is shared or should be shareable with other services as well. And this brings us essentially back to this image that we had in the beginning, where we might have other editors that interact with the same model underneath the hood as the diagram editor. So for instance, if you have here a form-based UI, here a diagram, and here textual files, they now all connect, for instance, to their respective services, like here the GLSP server that we just talked about, the LSP server that we also introduced. Something similar you can imagine is also existing for forms, but now they all operate on the same model. So when I change something here, I want to directly see the change reflected in the other side of the editor or in the other type of editor as well, and vice versa. So how do we solve that? Obviously, we don't want to integrate those services with each other because that would be sort of a mess, not scaling really well. If you have 10 of those, then you would have to have 2 to the 10 of integrations. Not quite, but nevertheless, so what's better solution is obviously to have another component that coordinates the state between those different services, and that's the model server. So just real quick, what the model server is sort of an own component that manages the runtime state of all loaded models so that they can be shared across multiple services. The model server provides a command-based change interface with notification mechanism so that these connected servers can synchronize and react to changes if they like. The other aspect that the model server provides, and that's really important, especially for languages like UML, is that it also encapsulates language-specific commands, because quite often, if you think of such a UI, you can trigger very similar commands if you create, for instance, a node here, or if you right-click in the tree and say new node here. This should eventually trigger the same command, which is creating a new node. So you don't want to re-implement those in each of those services, for instance, in the GLSP server or in the JSON Forms server, but you really want to implement them once so that they can be shared across all of them. And that's also what the model server provides. The model server is written in Java, mainly to allow reusing EMF, which is a really nice framework that you might be already familiar with, and then provides some sort of REST API for different actions like creating, updating, and patching resources. It provides multi-format support, so you can request the models here either in XML or in JSON to basically accommodate different types of clients like Java or JavaScript-based clients. I will jump through that really quick just to give you an idea. So basically the services can subscribe to, can load a model and then subscribe to changes. And whenever some of these services wants to change the underlying model, they send a command request to the model server. The model server will then actually run those changes and then obviously notify all the other services that this command has been now applied, so that they can basically, in the GLSP case, just do the same dance again that we had before, get the new model, translate it into a G-graph and a graph model, send it to the client and update the diagram. And with that, basically the rationale and the basic functionality of the model server is, I think, explained. I guess Nina will shake her head and will say, oh, that's forgetting like 50 of the most important features of the model server, but as an old man like me, I can kind of forget about these very important other features just for now to make the point what the model server is in terms of responsibilities. Right, coming back to the responsibilities. So really the model server is about what is the current model state, how can I manipulate the model. GLSP server is basically about where do I get the model originally from based on a URI, and how do I translate that into a graph model, which is then shared with the client, and how do I react to diagram specific requests based on that graph model. So for instance, how do I react if a label is edited, or how do I resolve a target from one element, a navigation target from one element to another, stuff like that. And the GLSP client is really only focused on rendering diagrams, which is translating graph models into SVG and handling user interactions. Before I hand over to then I think not Nina, but Julian, just a few key characteristics about the framework. So these are really all of those frameworks that we've talked about are programming frameworks. So you don't build a declarative model and then generate some code or so. I'm just saying because many of the diagram editor frameworks have been built this way. GLSP and the model server is really not about that. It really is just a programming framework that also puts no additional abstraction layers on top. So the disadvantages is that you get in touch with the actual low-level technologies like SVG and CSS and stuff like that. But the benefit is you get the full power of these underlying frameworks. We figured that's the better approach, since diagram editors especially are something very domain specific. So everyone wants to have full control over how they look and how they feel. That means you need to provide them access to the full underlying framework capabilities. Also, customizability, as I just mentioned, domain-specific tools, super important. Basically, all our customers are require the full flexibility when defining the look and feel of their diagram editors or of the models they load and they work with. So we really allow as much as possible customizability in these open source frameworks that we just discussed based on this 80-20 rule. So we provide access to everything, which is kind of overwhelming in the beginning because you could change everything. But there is default implementations for 80% of those things. So you can even change those default implementations, obviously, but there is default implementations, and typically you want to then fulfill the domain-specific 20% for which no domain-specific implementation or generic default implementations exist. What's really cool, I think, is that you can, with that, arbitrarily be flexible in your implementation, and also based on the whole architecture, arbitrarily combine platforms like VSCode, Eclipse, Thea, and so on with different model servers, with different GLSP servers, and so on and so forth. And with that, eventually, hopefully bring UML to VSCode. That's basically it from my side. Sorry, I hope I was sort of in time. I tried to be fast.